Hello everyone, and welcome to another GIS lecture video. In this lecture video, I want to begin our discussion talking about location and distance on a three-dimensional Earth. So, sort of the big concept here is going to be talking about how we go about recording a location on a three-dimensional sphere and using a three-dimensional sphere to represent Earth, and what those measurements that we're recording, what they actually mean relative to how we can use them to identify a location. And so the first thing I want to work through is this idea that we can think of the Earth as a sphere, right? And so if you think about the globe, right, everybody's hopefully seen a globe at least once in their life, right? That it is, right, largely depicted as sort of this perfect spherical shape, right? That we usually will depict Earth as this idea of sort of a perfect sphere, right? We depict Earth as sort of this, right? Perfect sphere. Well, what does it mean when we say that it's a perfect sphere? What we mean that the radius of the sphere, or the radius of the Earth, is the same around the middle as it is going from pole to pole, right? So when we say perfect sphere, what we mean is that the radius in the middle is the same, right, as the radius through the poles. Oh, sorry. Poles, right? That if we were to take a measurement from here, going along this line to here, right, we would get the same distance as if we took a measurement from here along this line to here. Right? That's what we mean when we say the Earth is a perfect sphere. Now, in reality, right, if we were to look at the actual Earth, right, there are two sort of deviations from the perfect sphere, right? So deviations from a perfect sphere. Right, and there are two things that we kind of have to think about here. The first, right, is that the sort of pull of gravity on Earth is not equal in both directions, right? So one, right, the pull of gravity is not equal in both directions, meaning, right, that the Earth, right, if this, right, is a perfect sphere, right, I'll put this as PS for perfect sphere, right, in reality, what happens with the Earth is gravity is actually pulling harder north and south on the poles than it is east to west along the equator. And so what you end up with, right, is Earth is actually, now I'm exaggerating here, right, Earth. Now again, I'm exaggerating here, but Earth is sort of squashed. So it's shorter pole to pole than it is through the middle, right? So in reality, Earth deviates from this assumption here, right? This distance from pole to pole is shorter than the distance going around the center. Right? The other thing with Earth, if you think about this for any length of time, right, you'll know that, right, the Earth has mountains, it has valleys, and some of them are quite considerable deviations. So, right, again, the perfect sphere, right, we would assume is this sort of uniform, every point on the sphere is equally distant from the center, right? The reality of Earth, not only is it sort of squashed at the poles, but it's also lumpy, right? And I'm exaggerating here, right? So the Earth is squished at the poles and it's lumpy due to variations in plate tectonics, due to differences in the mass density of different portions of the Earth's crust, right? The Earth is not this perfect sphere. It's pulled in more at the poles, and it has these sort of tectonic and geologic variations in the crust. But long story short, we assume a perfect sphere, meaning we assume that the rate that every point on the Earth's surface is equally distant from the center, and that the radius north to south matches the radius east to west. So what does that allow us to do? Why are we making that assumption? Well, by making that assumption, right, we have the capacity to actually measure with relative ease the location on a sphere. Right, and so what I've done is I've replicated that drawing with a little bit better accuracy here. Right, and what you'll notice is that with the Earth, right, again, this is a perfect sphere. Right, that we can divide the Earth, or in this case, our perfect sphere representation of the Earth, right, we can divide that into pieces. Right, and what you'll notice here, right, is that we have this line going through the center here. Right, this line going through the center, right, we call this line the equator. Right, and what the equator does is the equator divides the Earth in half. Right, it divides it in half through the middle. And so north of the equator, right, you have the northern hemisphere. Right, south of the equator, right, you have the southern hemisphere. Right, and so with one dividing line cutting the Earth in half, right, we're able to determine whether you're north of the equator in the north half, or you're south of the equator in the southern half. So we've already narrowed the position down by half, right? We can say that we're north of the equator or we're south of the equator. Okay? But we can do one more, right? We can do something else. We can divide again, right? We have this line here running north, south, right? This north, south line. Right? We call this the prime meridian. Actually, for the sake of illustrative purposes, let me move this down a little bit. Right? We have the prime meridian. And so, right, what we can do with the prime meridian is we can say, okay, well, if we are on this side of the prime meridian, right, we're in the eastern hemisphere. Western hemisphere, because we're going west. Right? If we're on this side of the prime meridian, we are on the western hemisphere. Right? And if we are on this side of the prime meridian, right, we're in the eastern hemisphere. Right? And so with simply two reference lines, one cutting Earth in half north and south, one cutting Earth in half east and west, we're able to determine, right, whether or not we're northeast, southwest, northwest, southeast, right? So with just these two lines of reference and no other information at all, we've already broken down our location into quarters. So we can be confident that we're in 1/4 of the Earth with no other information whatsoever. And it turns out that these reference lines, right, the equator and the prime meridian, play a crucial role in being able to take it a step further and actually be able to narrow down our location precisely. So what we're going to do is talk about how we can do that using angles. So let's focus first on the equator. So let's pretend for a second that we've cut the Earth in half so that we have a horizontal line cutting a circle through the center. So this horizontal line right here represents the equator. So this horizontal line here would represent this line here. So we've cut the Earth in half. We now have the equator represented as a straight horizontal line cutting the circle into two pieces, south and north. And let's imagine, for the sake of argument, right, that you are standing somewhere on Earth on this circle. So this point right here will represent you. What we can do is we can use the relationship between you, the equator, and the center of the Earth to create an angle, right? So we can go from the equator, we can go along the equator to the center of the Earth, and from the center of the Earth to you, right? And we can create an angle here. And so we call this angle between the equator, the center of the Earth, and you, we call this angle latitude. All right. So put another way, latitude measures your angle. Actually, let's do that in a different color so we can make this a little more clear. Right? Latitude measures your angle north or south relative to the equator. Right? So relative to this horizontal line that cuts the Earth directly in half, latitude measures your angle north or south relative to this equator. And so whenever you hear latitude, think north or south. Now, you will also sometimes see latitude represented in a slightly different way. You will sometimes, in mathematical equations, or if you ever go farther into geospatial science, when you're actually dealing with the mathematics of polar coordinates, you might see latitude referred to as phi or phi, and written like this. So this symbol, or phi, means latitude. So this symbol, or phi, means latitude. Whenever we talk about latitude, we're talking about the measure between you on the Earth's surface, north or south of an equator. So let's talk about this latitude, or phi, a little bit more detail. All right, so we already know, right, that latitude measures your angle relative to the equator north or relative to the equator south. But let's go ahead and talk about, right, the appropriate range of latitude. Right, so when we're talking about latitude, what can we reasonably expect latitude to be? So let's go ahead and work under the assumption that, right, if we call this angle here, right, where you are on the equator, if we call that 0 degrees latitude, which makes sense, right? Because the angle between you and the equator in that case would be 0, right? As we progress north, right, along the Earth's surface relative to the equator, right, this is going to be increasing latitude, right? So with increasing latitude, right, you will see this represented as a positive number. Oops. You will see this represented as a positive number. Or you will see this represented with a degree sign, N, for degrees north of the equator. So you'll either see a positive number or degrees N. So if you see a positive number, you can assume that we're going north along the equator. Now we keep going, 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 all the way until we hit, right, the North Pole. I'll go ahead and switch colors for a second here. Right, we hit the North Pole. Right, the farthest north you can go before you start decreasing in latitude again. Once you hit the North Pole, right, once you hit the North Pole, right, if we measure this angle out, because again, right, latitude is the measure between the equator and you, right, once we hit the North Pole, this angle becomes 90 degrees, right? And so if we define being at the equator as 0, going north along the Earth's surface to the North Pole, right, we would define the North Pole as 90 degrees north, right? So we know that the maximum value of latitude, right? So we know that the maximum value of latitude right, is 90 degrees north, and you'll see that it's a positive 90. Okay. So let's talk about what happens the other way. So let's say that instead of going north of the equator along the Earth's surface, let's say that instead you decide you wanted to go south. Right, so you start from the equator and you start heading this direction. Right, well, this direction, right, you're decreasing latitude. Right, you're decreasing latitude as you head south of the equator. And so the way that we represent that is either with a negative number, right? So if we're doing math, right, heading south of the equator would equate to a negative latitude, or you'll see it with a degree sign and then south. So you'll either see a negative number or a degrees south. So if you ever see negative, assume that you're going south of the equator. Right, so let's do the same thing we did before. Let's assume that we keep going and we keep going and we keep going and we keep going and we keep going until suddenly, right, we hit, right, the South Pole. Right, and so we know, right, again, the definition of latitude, right, is your distance north or south of the equator. Right, and so if we draw the angle between the equator and you standing at the South Pole, right? By definition, we're going to get a 90-degree angle. Right? So when we do that, what we end up with, right, is a 90-degree angle, right? Just like up here, a 90-degree angle, but, right, because we went south of the equator, right, it's 90 degrees south, or, and this is the or part, negative 90 degrees, right? Because south means negative number. So let's then talk about what happens if we kept going, right? We hit the South Pole and we go this way, right? What happens if we keep going, right? Well, if we think about this measurement, right, relative to the latitude measured against the equator, right, going this way is the same, right, as measuring from this direction, right? So if we were to end up here, right, we could measure all the way like that, but we don't. Instead, what we do is we measure coming from this direction, right? So the minimum value that we can go, right, south is negative 90 or 90 degrees south. If we go past that, right, we're going back up again. And so we measure from this way, if that makes sense. Right? So the minimum value the minimum value, let's try and clean that up a little bit here. Right? The minimum value of latitude right, is 90 degrees south, or put another way, negative 90 degrees, right? So in essence, latitude goes from negative 90 degrees to positive 90 degrees. So if you ever see latitude outside of these ranges, you know that it is an invalid measurement. So that's the first measurement. We can measure relative to the equator. But if we remember back, right, we have, if we go back a couple slides, right, you know that we can measure relative to this line, right, but we also know that we can measure relative to this line. Right? And so what we can do is we can do much the same thing as we did here, but we can break it up this way, right, where we take the Earth, cut it in half, and then we have a line running north-south that splits the circle into an east half and a west half, right? And again, we call this line the prime meridian. And so we can do largely the same thing that we did for dealing with. We can do largely the same thing we did dealing with the latitude, right? Is we can take the measure of the angle of U relative to, right, this prime meridian. Right, so we can take this angle here between U and the prime meridian, and we call this angle longitude, or sometimes you will see it referred to as lambda. Sometimes you will see it referred to as lambda, or drawn out with this symbol. So if you see this symbol, the word lambda or longitude, right, know that what we're referring to by definition, right, is the angle right, between U and the prime meridian. Right, the angle between U and the prime meridian is our definition for longitude. You'll often see this represented with the word lambda or this symbol here when you're dealing with mathematics. So let's go ahead and look at sort of the limits or acceptable ranges on longitude. Right, what can longitude do? What acceptable values can it take given a point? Right, so we already know that by definition, right, this angle here is called longitude. So let's go ahead and do what we did before. And let's assume that we start right here, right, where your position is the same as the line that encompasses the prime meridian. Right, we define this value here, right, as 0 degrees longitude. Right, and as we go east, so to the right of the prime meridian, right, as we go east, right, of the prime meridian, right, this is increasing longitude. Right, meaning, right, that we represent this going east of the prime meridian as increasing longitude. So we represent this with positive numbers. Or you will see this with a degree sign and then an E. So anytime you see degrees east or a positive number in reference to longitude, you know that we're talking about going east of the prime meridian. Right. So let's talk about then what happens if we keep going. Right. If we keep going and we keep going and we keep going and we keep going, keep going, and we keep going, right, until we hit this point here. Right. So with longitude, what happens is we continue all the way around until we hit where the prime meridian meets the other side of the Earth here, right? We define this point as 180 degrees longitude, right? And so what we can infer from that, right, is that the minimum longitude, right, is 0 degrees, right, east or 0 degrees west. Right. As we go around and around and around and around, right, we hit the maximum longitude. Right, which is 180 degrees, right, east or west. East or west. Right, and so the way that we get west would be, right, if we started at the prime meridian, right, and we were to travel this way, right, as we do this, right, we get decreasing longitude. right? Decreasing longitude. So we represent this decrease in longitude by negative numbers. By negative numbers. Or by degrees. By degrees west. So if you see a negative number in reference to longitude, you know you're heading west of the prime meridian. If you see degrees west, note that we're talking about negative longitude. Right? And so the minimum value is actually negative 180 degrees west. Right? So put another way, right? Longitude longitude, right, can go from negative 180 or 180 degrees west to positive 180 degrees or 180 degrees east. Okay, so latitude measures the angle relative to the equator and measures from negative 90 to positive 90. Longitude measures the angle relative to the prime meridian, and it goes from negative 180 to 180. Hopefully that makes sense. And if you have any questions, as always, please reach out. Thank you.